Thank you. Super excited to be here. This is actually my first real talk after more than 3 years. So bear with me as I'm learning how to give a talk. Okay, so I'm going to talk about embodiment in AI. Most of the stuff that I'm going to talk about today is not new, but putting them together is probably would be the next big challenge in AI and next big step. And that's going to be the theme of my talk. For this audience, I don't need to spend a lot of time re-emphasizing how important integrated AI is in our life. It's in our home, on our hand, in our breast, in our face, even in our ears, in our cars. As a matter of fact, there are probably more than a few hundreds of AI algorithms running in our pockets as we speak. So it's everywhere in our life. And it's not just our life, right? Our work. So today we saw an amazing set of things in the morning. I'm actually excited to hear more of this theme in the afternoon, that AI helps scientific discovery of different forms. All super exciting. And it's been an amazing progress so far. So to me, this is sort of my favorite example, these kind of examples to show progress in AI. This is a visualization of a new system called DALL-E, the version 2 of DALL-E. It renders images for query text or the other way around. And you could think it to various different queries. So Noah Smith, our colleagues, put this as a painting of a few professors walking in the University of Washington and do it in a surreal style. You could actually see that this system knows a lot about our work. If you look from distance, this kind of looks like Europe. We can debate if those folks look like professors or not, but certainly the system knows about George Sorai's style. So a lot has actually been encoded in these systems. And that to me looks like an amazing progress. The system actually knows about us today. So if you ask for an exciting Europe presentation about AI, you actually could see a start, like these are the top 10 pictures generated. The one in the top corner would be a good example. So these are sort of truly generated by an AI system. It could see that there are people are actually looking at the audience are engaged. So there's so many subtle things about our words that are already encoded in these models. It's actually mind-blowing to see the pace of progress that gets us to this point. It also knows about realities. So a boring presentation by your professor about AI. And you could see the change, right? It's now a slide. People's necks are still tilted. And I never typed in artificial intelligence, but you could actually, if you squint from distance, you could see the words or letters that resemble AI on this slide. So lots of exciting things happening. I don't want to spend a lot of time on this topic, but rather go to sort of under the hood and understand what's going on with gross oversimplification. So most of these systems look like this. There is a network. This is a neural network, a set of weights that represent that network. It can encode various different input, and it can produce all sort of outputs. You can feed in an image, get an image at outside, feed in a text, get an image, feed in a text, get another text, label things, understand it, detect things. You can actually provide time series and get different kind of output data from them. And again, if I want to oversimplify things one step further, the pipeline oftentimes looks like this. And that's sort of the slide that I'm going to spend most of my today on. We collect data, we annotate it, we train models. If we want to be super careful, we evaluate them and test them in various different conditions, and then we deploy. So what I'm arguing for is that we kind of figure out this model, meaning that if the domain is actually confined within our controlled environment, our comfort zone, we kind of know how to do that. And that oftentimes would take the form of a web-based data, web-based annotation, train a model on your servers, and then test it and then deploy it the same way. Image, you have seen so many examples of those already happening around us. I think that the hallmark of this progress to me is this plot, sort of reassuring that we kind of figure out how to deal with this problem. So what I'm showing is over a decade, progress in one of these benchmarks. This one specifically is ImageNet, 1,000 class classification problem, fit an image, get a label out. You could see the progress has been amazing. So a few things that we have learned along the way. One is that scale goes a long way. The second one is we've been, at least I've been consistently wrong in predicting the pace at which the progress happens. It happened way, way faster than we thought it would happen. But right now, if you look at those numbers are actually 99 something. And if you care about actually the winning models in this very, very tough competition, it is actually coming from Europe collaborations. It's sort of reassuring that we kind of know how to do these problems. If I know the domain in which I'm going to operate, if this actually happens within these web scrape domains of AI applications, we kind of know how to deal with this. There are so many other problems around it that I don't want to get into it because I believe there is a bigger problem to catch. And that problem is when we want to get out of our comfort zone, when we're going to actually go to the real world, deploy things in the real world. And roboticists in the room are very, very comfortable and familiar with this topic. And I'm going to actually spend a lot of time on talking about this whole notion that now I'm going to actually get out of my web-enabled AI solutions, go to an embodied solution, and talk a little bit about what it entails, what breaks, and what can we do to fix that. And my punchline, if I want to say that at the very beginning of my talk, is that I do believe this is actually the next big step in the AI. Embodiment is going to actually resolve many key blockers in our systems. And it's going to actually open the doors to many, many different kinds of applications. You could ask, aren't we already doing this? We actually have cars moving around. And actually, I agree with you. We actually are moving in that direction. Our solution oftentimes looks like this. I still have my standard comfort zone. What I do is I actually deploy my model in the real world. For many cases, it might work well. For some, it might not. I actually want to borrow a recent result from our colleagues. Well, my slides are broken. From Alex Fang, Simon, and Ludwig. Again, another set of results that shows that sometimes progress in our web scrape databases does not necessarily translate to the same amount of progress in real world. Sometimes it correlates with it in most of the cases. And sometimes, for example, the one in the middle, in the bottom row, it actually hurts. And I wanted to scratch my head and think a little bit more about why is this? What's going on? One could argue that, well, maybe there's a discrepancy between these data. They're coming from different distributions. There's a distribution shift. There are gaps in the data. And let's actually go through them little by little. So first thing we can do to fix this problem is, well, let me actually collect my data the same way I'm going to test this. So I'm going to actually move my data collection out of my computer. Now my deployment is already out. And now I can start training these models again. Issues? Well, it's actually really hard to enforce that these data are similar, especially if I'm deploying in the real world. I don't know by construction and by design, I don't know what's going to happen. More often than not, my data is not going to look like what I've collected and what I've trained the models on. So one key principle that we should spend a lot of time on is this whole notion of adaptability. How can I adapt to an ongoing change in the environment, knowing that I should assure myself I won't be able to control all what's happening in the real world at deployment time. And there are different ways to think about it. But the issue is that this change, this adaptation is very costly. Some of these models that we work on, if I want to train them once, I actually have to deal with a hefty cost. For the large language models these days, we're spending something in $10 to $20 million if I want to train one of these models. For the clip model, the kind of model that I showed visualization results off of them, if I want to train those guys, if I have a single GPU, I'm looking into sort of 29 years. And if I'm fortunate enough to have 600 GPUs lurking around, I might be able to do it in less than a month. So it's very, very expensive to update these models. Also, even if I manage to update them, we're dealing with a problem known as forgetting. As I teach these models new concepts, they keep forgetting the old ones. And it's a hard phenomenon to deal with. So think about it. I'm deploying a model out there. I realize that my model is actually not working really perfectly in, let's say, the ASR system, in this specific kind of accent. I train a model for that accent. At the cost of, I might actually forget or regress in some of the behaviors of the old model. How can we fix that problem? I don't believe there exists a fix for it right now, but sort of we started to barely scratch the surface. Franklin et al. A couple of years ago discovered a very interesting phenomenon. If you train neural networks in specific ways, that I don't want to get into that, especially if they have a shared backbone, and then you start training two models, let's say theta 1 and theta 2, and then draw a line between them. Points that appear in that line actually belong to a neural network. I've never trained them, but I could actually sample along those lines, and that could actually be a decent neural network. As a matter of fact, sometimes it might be a network better than the two endpoints. Combine that idea with the idea of these large-scale pre-trained models, the models that I just explained how expensive they are. These models expose very, very interesting properties. They are very versatile, meaning that I could actually pre-train them once and apply them to a wide range of tasks. They're fairly robust, but they need to be fine-tuned to my task. So if I combine these two ideas together, then my theta 1 might be one of these very expensive ones. My theta 2 can be the task that I would like to train with. And all I need to do is to find the right way of finding the controlling interpolation parameter between these two data points. And what that gives me might be a decent model that serves both purposes. Here's a quick test. I have in-domain data, let's say D, out-of-domain data D prime, and ideally I would like to actually stay in this line. And there are evidence that humans actually do stay in this line. Now, here's here's the line where I actually tune a model in domain only. And here the stars are the expensive pre-trained models. They're better in robustness or out-of-domain distribution. They're worse in domain distribution. And let me zoom in this part. So let's do that trick. I can actually go to the weight space, figure out with ways that I'm not going to explain the right parameters, and interpolate between them. What's going to happen is that if I just purely fine-tune, I'm going to arrive at this point. I'm going to improve in domain accuracy with a good cost of out-of-domain. But if I do it the way that I explained, I'm going to actually arrive at a curve that looks like this. It is interesting. It behaves in ways that we actually don't truly understand, because by doing this way, we're improving on both axes. We're improving robustness while also improving the in-domain accuracies. And if I zoom out, this is sort of how this curve would look like. So looks like there are ways that we might be able to adapt to issues that we have in discrepancies between when I train the model and when I'm deploying it. However, the issue is that those solutions are still fairly expensive. And I think one big challenge for us is how can we find solutions to that? The other common problem with embodiment is a notion we tend to call it model patching. We're pretty much guaranteed that we cannot think of all possible scenarios that could go wrong at deployment time. As a result, we should be able to actually find a way to patch our models along the way. And there are interesting solutions that we have seen out there that sort of resembles this patching solutions. I have a known set of things or tasks. I have an unknown set of tasks. And what I would like to do is sort of get to that point. I'm not going to go through the details of that, but it turns out that the same kind of tricks that I just explained in weight space ensembling also extend to this, to the extent that I should be able to start from one of those pre-trained zero-shot models and expand it in multiple different directions, each of which expose the properties that I've explained. But now I can actually do it collectively across multiple different tasks. Let me go back to this. The other issue that we have is the worst changes. And sometimes these changes are not actually to be predicted. For example, if you were working on face recognition and detection 3-4 years ago, you would have thought that the problem is solved. Suddenly we woke up one day and there were masks on all faces. And if you were using any of these things on your phone, nothing worked. And have you noticed how long it will take us to actually fix that problem? Quite a long time. The issue was these updates were hard. And we wanted to be able to actually adapt to new environments fairly rapidly. This is sort of, and the issue that we have right now is this rigid definition that we have in machine learning. We have train time, where we train the object models, and then we have inference time, When we teach machine learning, we actually doubly emphasize, make sure that you don't train on the test set, because then your numbers are not going to be reliable. That's a big principle in machine learning. We're going to stand by it, but that's also a big problem, because this is not the way embodied and intelligent solutions should actually work. They should be constantly learning. Here's my one example that I'd like to explain. So here, this gentleman is probably walking for the first time in rain. Muddy puddles are exciting things to him. As you could see, he's starting to feel some issues with control. He's struggling with actually walking in this muddy puddle for reasons, because it's a new environment, it needs to adapt to it. But it would only took him 2 or 3 trials till he figures out, oh, I know how to fix my problem at such a speed. Like, just the space is phenomenal. When he figures it out, look at the smile in his face. So it's actually, this is what I'm talking about. The whole notion of train and test is completely submerged. This gentleman didn't have a train phase where we're going to actually froze all the parameters in his head and then move to a test phase where I'm going to actually only run inference. How can we do this for our AI? And again, the answer is we don't know. There are some small solutions that scratches the surface. One of them we call learning to learn how to learn. And the idea is, well, what you want to do is at train time, not only you want to optimize your objective function and you optimize your loss, so you actually have a match between your supervised loss, unsupervised loss, semi-supervised loss, but also you want to be prepared to learn how to learn at inference time. Can I actually encode something that helps me learn at inference time? It turns out that yes, you could actually start encoding very interesting phenomena, and it will be fascinating to talk at some point later about what kind of things you could learn that way. For the sake of time, let me actually skip this one. Let me go back to this slide. So we talked about this pipeline as sort of the common pipeline. But that is not it, actually. I was lying about this pipeline. This pipeline has a lot more to it from both sides. Very quickly, let me actually touch upon one side, and we've seen a little bit of this in the morning in one of the institutes that people were talking about. Once I have a model, I need to deploy it on a piece of compute platform. And now my compute platforms have all sorts of its own restrictions. How fast can I run? How much battery do I have? Do I need to slow things down because I'm low on battery, et cetera, et cetera? There is a whole area of work, very exciting area, just started, and it's a lot of excitement in that space. Nice collaborations between physicists, electrical engineers, and computer scientists. To me, the key to the success of this part is that this piece needs to be trained with the rest of the system. If we think about it, that I'm going to actually have this model, here's the architecture, now I'm going to actually be creative about how to deploy it, I think that whole pipeline is broken. Here's one example. That why we need to start baking in this kind of adaptivity at the training time. When you think about our representations, oftentimes they're fixed. They are k-dimensional vectors. We call it representations of objects, words, languages, audio signal, etc. These are fixed dimensions, and these are oftentimes flat. That means that at inference time, if for whatever reason I need to adapt to a smaller feature vector, I don't have a way to do that. You could actually bake that into your network. You can actually train solutions with this nested architecture. And then when you're going to deploy them, you can actually benefit from multiple X speed up, both in terms of the index that you need to use and also inference time speed up. A whole active area of work. I don't want to actually spend a lot of time on it, but I believe that would be a big next step. I want to spend the rest of my time on this side of the story. Before we even start collecting the data, oftentimes when we start thinking about it, we assume that we're given a system in the embodiment. I have this car, I have this camera, I have this microphone, and they're frozen as well. My camera parameters, my camera design structure is frozen. And now I'm going to actually sort of go work with my models to be able to improve this. Oftentimes in AI, or almost every time in AI, we think about progress as improving the intelligence. Bigger brains, bigger models, higher accuracy on the test set. That's sort of how we measure AI. And I showed this slide at the beginning that exactly resembled that. Even if you actually do, yesterday I did the Google image search on AI, look at the images. They're all examples of brain of some form. So this is sort of how we think about intelligence, and nature might disagree. So the optimal solutions that we have in nature is actually a combination of intelligence among many other key properties. And success oftentimes does not actually necessarily mean more intelligence. What I'm arguing for is that instead of just fine-tuning our parameters for a better model and higher accuracy, we actually need to find a way to optimize for a whole gamut of other parameters that we need to encode. So thinking about this, yes, we have to optimize for strategy, and we've been doing this. We kind of know how to do it. There are challenges, but also sensory and physiology. And if I have those parameters to optimize for, maybe my autonomous vehicle might not even have a wheel underneath. And I don't know what sensors might be the right sensors to deal with them. Let's see a quick toy example. I'm going to grossly over-parameterize these things. So I have an area of view for sensory. I have a decay of how long you're going to look into the future as a strategy, and a speed for physiology. And I'm going to actually have super simplified word. I have a prey and a predator in a closed environment with some random obstacles. And now we're going to, because these have, this includes evolutionary items and also machine learning. So I'm going to actually combine short-term learning, which is what we do, with long-term learning, evolution, and combine them together and see what we can actually learn in this space. So you can move around, you could see for both of them, and can actually train these agents together. The big question we had is, can we start thinking about what would be the optimal solution? And the optimal solutions that popped out was sort of kind of what we were expecting and aligned with the biological understanding of evolution. For example, if you actually have low sensory capability, the one on your left, it doesn't matter how smart you are. Your success rate would not translate, your higher intelligence would not translate to higher success rate if you actually cannot sense the world at the capacity that you would like to. Let me skip to this and just talk about this one. I could actually now put all these parameters together in the form of energy-based optimization, right? There's a cost for improving my vision. There's a cost for improving my speed, my intelligence. If I want to optimize them together, what would they arrive at? So when the cost for speed, when the cost for intelligence and the cost for vision or sensor is low, you actually arrive at creatures that look like dogs. When the cost for vision, let's say, is high, you're under the water, you actually, it's hard to develop a sensing for whatever reasons, then intelligence won't matter. And now we're actually start to learning behaviors very similar to what actually happened for fish. And these are sort of reaffirming some very interesting evolutionary biology theories that talks about the evolution of fish. So one data point to explain how these things connect together. And what I'm arguing for is that instead of just fixating on intelligence, for embodied AI, we actually need to figure out a way to optimize for all of these things together. And again, this is also an oversimplification at this point, because there's a whole environment at which these agents are going to operate. There are a whole set of other agents in this environment, and we need to actually figure out how we're going to optimize them together. So let me go back to my slide that I said this is the pipeline. I lied again, because to me, actually, that pipeline looks like this. These things are connected to it. We like it or not, the way that I'm going to annotate my data actually depends on the compute platform that I'm going to run this thing on. The design decision of my embodied the agent, whatever it is, it's a speaker in your home, it's a watch in your wrist, it's a cell phone in your pocket, it's an autonomous agent out there in the world, it's a factory line, a robot. All of them actually have this very intertwined set of parameters. We still don't know how to optimize together. And my most important message of the day is this. If you look, a good portion of these edges are actually multidisciplinary. Computer scientists, we actually don't know how to solve some of these edges. And some of these edges are well studied in other disciplines. So what I'm actually calling for is a cross-campus, multidisciplinary research between biologists, mechanical engineers, electrical engineers, physicists, computer scientists, electrical engineers, to put all of this together so we actually have a holistic framework that we could optimize for all of these parameters together. Again, I'm going to reemphasize that I'm actually putting my money on embodied AI as the next big challenge and big step in AI. This is a problem that is cross-disciplinary in nature, but also It's cross-disciplinary at the very bottom of the stack. We actually have to start optimizing and learn these things together from the very, very, very bottom of the stack. We need to figure out a solution for this problem of adaptivity. We need to figure out a way to build solutions that are always learning. And for all of these bullet points, there is sporadic evidence that we could do some of these things in isolation, but we need to figure out a way to do all of them together. The bigger problem outside computer science is arriving at this parametric model that explains the world and entities. So we could actually get those parameters and optimize them. And then thinking about true end-to-end solutions. We talk about end-to-end, but our end-to-end is actually not truly end-to-end. End-to-end goes all the way to the rays that comes into in the word and the audio waves, all the way to how we're thinking about the silicon. And one key step that we've learned repeatedly is that scale matters. And scale is going to be a challenge for academic institutes. But if you want to actually be part of the game, we need to figure out a solution for a scale. With that, and with being grossly over time, I'm going to end. Thank you.